Hello everyone, my name is Dawood. I am from Iowa State University in the United States, and my presentation is about distributed non-convex optimization problem. And this is a joint work with my advisor, Dr. Mingyi Han and Mingming Zhao from Zhejiang University in China. So first of all, let me give you a brief introduction of distributed optimization problem. So in distributed optimization problem, we have a connected network of agents like this picture. And each agent contains a local cost function which is denoted by phi of x. However, each agent has a partial knowledge about the entire problem. So no one knows the entire problem. Okay? And the key objective of the individual agents is two things. Number one, each agent is trying to achieve consensus with the optimization variable with its neighbors. And second, the agent's goal is to optimize the global objective function summation of phi of x. Okay? So why this is an important problem? Why do we have to study this problem? In the following, I will give you some reasons. So first, consider this the data optimization problem in which the data sets, the data points are gathered using distributed agents in different parts of the world. Okay? And it is infeasible or inefficient to collect all of this data in a central location. Okay? So in these cases, one alternative is to do distributed optimization solution problem. And second reason is related to the data volume issue. So the data volume is growing very fast. So look at this picture, and you see that the data volume is growing too fast. And in 2025, it is predicted that the data volume would be 180 zettabyte, which is 180 followed by 21 zeros. So in many cases, it is impossible to do centralized computations. Okay, so we have to do distributed computations. Okay, so now let's see why non-convex distributed optimization problem is important. What are the motivation for studying this non-convex problem? Let me give you an example. The example is distributed binary classification. So we have a network of sensors. These are connected together, and each agent contains this local cost function. Okay, this is a non-convex function. Okay, so the question is that can we apply the existing algorithms which has been designed for convex distributed problem? And the answer is no. So for example, for this non-convex problem that I just showed you, we have applied distributed subgradient algorithm. And here is the results. So you see that for different step sizes, the algorithm is not converging. Okay? So the challenges and open question in this area are the following. So the question is that can we apply convex distributed algorithms to the non-convex distributed problems? And is there any convergence guarantee for the algorithms? And how fast are these algorithms? So considering this question, our contribution in this research is the following. So first, we're going to design an optimization algorithm to solve distributed non-convex optimization problems. We provide convergence analysis as well as rate of convergence for this proposed algorithm. Okay, so let's briefly review the literature for distributed optimization problem. The literature is split into two parts, in convex cases and in non-convex cases. In convex cases, the literature is very extensive. So for fully distributed network, by fully distributed I mean that the agents in the network are identical. There is no particular node in the network. So the literature is very broad. I just pick a few more relevant works. The first work is the decentralized subgradient, which is designed in 2009. This algorithm needs diminishing step size to converge to the global solution, which is not good, and the convergence rate is very slow. It's log of r over the square root of r. R is denoting the iteration. The next algorithm is extra algorithm. This extra algorithm leverages the information from past two iterations. Okay, so the rate of convergence for this algorithm is 1 over r, which is much faster than the previous one. And however, this algorithm works only for convex cases. Okay. And another network topology is a network in which we have a central controller. This is more popular in the machine learning community, and there is some algorithms for this type of network, like ADMM, DANE algorithm, and DISCO algorithm. And but for the non-convex distributed optimization problem, we have only a few algorithms: U subgradient, ADMM algorithm, next algorithm, and nest algorithm. However, there is still a gap in the literature. The gap is that for non-convex, fully distributed optimization problem, there is no algorithm with global convergence rate. So in this research, we're going to fill this gap. Okay, so let's go to the next section. So so this is the contribution of our paper. So we proposed a primal-dual algorithm, which is called Prox-PDA, for non-convex problems over a fully distributed network. Then we provide convergence analysis and rate of convergence for the proposed algorithm. And finally, we propose some variants of the Prox-PDA algorithm to facilitate the practical implementation. Okay, so let's reformulate the problem first. The network that we have considered in our research is an undirected, static, and connected network. Okay, so for this problem, we split the global variable x into local copies of xi. So the original problem, we have summation of fi of x. Now we have summation of fi of xi. Okay, since we need consensus among all agents, we add this constraint: xi minus xj equals to 0 when the xi and xj are connected. Okay, since the entire network is connected, this is equivalent to the original optimization problem. And this optimization problem can be further simplified using some extra notations. For example, if we extract all the variable xi's into variable x and define a new function f of x as the summation of fi of xi, and also if we define a matrix which is called incidence matrix in the following way. So for each edge in the network, we have a row in the matrix, and for each node in the network, we have a column. So since this node is connected, this edge connected node 1 to node 2, we have 1 here for node 1 and -1 here for node 2. Okay, this is the same for the rest of the edges. So we can simply check that these two equations are equivalent. So here is the algorithm. The algorithm is an augmented Lagrangian based algorithm. Okay, so we define the augmented Lagrangian in relationship 3. And here is the algorithm. This is a primal step and this is a dual step. In primal step, we minimize the augmented Lagrangian plus a proximal term. Okay? And here is the dual step. So this proximal term is very critical in our algorithm because it ensures two important things. First, it makes the primal problem strongly convex and hence easily solvable. And second, it makes the primal problem decomposable over different variable blocks. Okay, this is very important. So let's see how it works. So if we define signed and signless Laplacian matrix in this way, and we define matrix B as the component-wise absolute value of matrix A, then the primal update can be written in this form. Okay? So the first term is decomposable, this is decomposable, this is decomposable, and the red term is also decomposable because D is a diagonal matrix. It is actually a degree matrix in the network. Okay. So now let's see the convergence analysis for the Prox-PDA algorithm. So first, let's see the assumptions. So the assumptions are very common assumptions for non-convex problems. So first assumption is that fx is an LS smooth, and also A transpose A plus B transpose B is greater than identity. And the second assumption is that f of x plus this term is lower bounded. So on the first step, we bound the descent of the augmented Lagrangian. Okay, so this is the lemma. If all the assumptions are satisfied, LR plus 1 minus LR is less than the right hand side. Okay, so we can see that this term can be negative, but this term, the coefficient in front of WR, cannot be negative. Okay, no matter how big beta are. So this L augmented Lagrangian cannot be served as a potential function. So we need to look for a different term. And it turns out that this term is our desirable term. Okay? So in this lemma, we can see that this term is decreasing in terms of WR and increasing in terms of XR plus or minus XR. It's basically behaving in an opposite manner of the augmented Lagrangian. And surprisingly, the conic combination of the augmented Lagrangian and this term can be served as a potential function. So we have defined the potential function as a conic combination of the augmented Lagrangian plus this term. And here is the result. The potential function is decreasing as long as beta and C are picked in an appropriate manner. Okay? And also we can simply show that this potential function is lower bounded. So if we define the optimality gap as the summation of the primal gap and the due gap, and we can simply check that if this goes to 0, Q goes to 0, the limit point of the algorithm is a KKT point of the problem. This is the main theorem. If all the assumptions are satisfied, we have the consensus, we have the convergence to the KKT, and also we have the sublinear convergence rate for the algorithm. So this term shows that the algorithm behaves in a sublinear manner. So here are some variants of the Prox-PDA. So in order to have a descent in the potential function, as I said, the beta should be picked large enough. But the lower bound for the beta needs some global information. It is difficult to calculate, okay? So in this case, we replace beta with some node-specific beta R, which is increasing. Okay, and second variant, in second variant, we just simply solve the primal variable, the primal problem using an inexact approximation. Okay. Okay. Now let's see some interesting connections between the existing algorithms and the Prox-PDA, which is the Primal-Dual Algorithm. So we can check that the Prox-PDA algorithm can be written as a primal only. Okay, this is a primal only for the Prox-PDA, and this is nothing but exactly the extra algorithm. So utilizing our analysis, now we can say that the extra algorithm can be applied to distributed non-convex optimization problems. And now let's see a few numerical results. We considered the distributed binary classification problem, and we measured the optimality gap and constant violation. So this red dashed line and this blue line are our algorithm, and the yellow is the DSG algorithm, and this one is the distributed push sum algorithm. You can see that in all cases, our algorithm is much faster than these two algorithms. So in conclusion, in this research, we propose a primal dual algorithm to solve a non-convex distributed optimization problem. We provide convergence analysis and convergence rate for the proposed algorithm. And finally, we have found some interesting connections between the primal algorithm and the primal dual algorithm.